Hi guys, number 2 in the series on metals, and in this particular video we're going to be looking at some common alloys. Now, one of the things that's very important when we start to look at alloys is that what we're trying to do here is to draw an improvement in the use of different types of metals by the addition of other elements. So an alloy is a mixture of different metals in varying combinations or proportions. Now, not all of the elements that are added to a particular metal to create an alloy are metals. So you can see one example of those down the bottom here. Carbon can actually be added to iron in order to create the alloy steel. And this particular alloy produces a substance which is much harder than the elemental iron. The two main types of alloys that are produced are homogeneous, homo meaning same, so these alloys are produced where the element that's being added, the metal that's being added is of a roughly similar size. So you can see in the first diagram, the zinc here has atoms that are roughly the same size as the copper, so it doesn't tend to change the overall nature of the substance. We've just substituted some of one atom with another, and so the whole thing just is reasonably consistent or homogeneous. That's not the case for steel, because in steel it's heterogeneous, it's different, and that's because the carbon atoms are quite different in size to those of the iron, and so they kind of sit in the little spaces, and that creates a slight difference in the way that the alloy actually works, and also, I guess, in its properties. These are not compounds, they are mixtures, and one of the main reasons that they are mixtures is that the proportions of the different components, proportions can change. Okay, we know in compounds are fixed ratios, but in a mixture you can have a change in the proportions, and we found that with our alloys, different proportions are going to slightly change the properties of each alloy. So why do we do it? Well, the main reason is that the presence of additional atoms in the crystal lattice change its properties. So we're looking for desired properties. And this is the reason why we produce alloys. When the crystal lattice is disturbed, so if you think about our metallic structure, our metallic crystal, we're talking about a group of positively charged metallic atoms or cations surrounded by a sea of electrons, which is our most common model for thinking about metals. We've got some of those cations of one particular type of atom being replaced by those of another. One of the consequences of this is that we get a range of changes in the properties, and these can include a change in color. So copper has a sort of a salmony pink color, but when we alloy it, we can change its color to yellow. We can also change the hardness. The addition of tungsten makes the steel much harder than just combining iron and carbon alone. We can reduce the malleability, the ability of the material to be shaped. The high carbon tool steel is less malleable than iron, so it doesn't it's not as easy to work with. It doesn't shape quite as well, but that can increase its strength. We can also change the electrical conductivity. Some of the cupro-nickel alloys and brass have lower electrical conductivity than the pure copper, which is the dominant metal in each of those alloys, and also a change in things like melting point. And we'll have a little bit of a look at solder later on as an example of an alloy that has a lower melting point than either of the two metals that are used in its construction. So let's have a look at a couple of these in a little bit more detail. Bronze we looked at very briefly in the previous video. This is an alloy of copper and tin. The Bronze Age was a very important age as we started to realize that there was some value in combining different types of metals together. The addition of the tin to the copper increased the strength, and this was the start of weaponry, as we started to realize that if we could strengthen these particular types of fairly soft metals, then we could actually improve the range of uses that we made of them. Another more ancient alloy, one that's not used very often anymore for obvious reasons, is pewter. And pewter is an alloy of lead and tin. Now the problem, of course, is that lead is very dense, one of the densest metals, but it's also very soft. So adding tin to the lead allowed it to be used in a variety of cooking utensils. But of course, if you're cooking your dinner, which you then plan to eat in containers made from lead, you are exposing yourself to a known carcinogen. So unfortunately, pewter hasn't managed to survive into the modern age. What we want to do is just have a look at a couple of these in just a little bit more detail. So firstly, let's look at steel. Steel is an alloy of iron and carbon, and the various different proportions of carbon and the addition of other elements as well changes the nature of the steel. The simplest form of steel is just pig iron that has about a 4% carbon content, and that's often what comes out of the smelters. And this can be recast. This pig iron, if it's melted and recast, then it produces what we call cast iron, and that can be used for gratings and things like that. The mild steel has a very small proportion of carbon, less than 0.2% of the alloy is carbon, and there's also just a little bit of manganese in there. It tends to be used for car bodies and also nuts and bolts and things of that nature. Structural steel, which is going to be a little bit harder, has a higher proportion of carbon in it and also a slightly higher proportion of the manganese. And as a consequence, we can use it for things like railway tracks, axles, those sorts of things. As we continue to increase the carbon content, we produce the really high carbon steels, ones that are much harder, and these are the ones that can be used for axe heads, scissors, other types of weaponry and those sorts of things. So these are much harder types of steel. You may also be familiar with stainless steel. Now, stainless steel is a variant of steel. It still has between 0.1 and 1.5% carbon, but it has a very high proportion of chromium and also the addition of nickel. And this changes its property quite considerably. So kitchen sinks and cutlery, things that are made out of stainless steel. Another one we want to have a quick look at is brass. Brass is an alloy of copper, but unlike bronze, in which we tend to find that zinc is the dominant metal combined with the copper, in the case of brass, it is zinc. Bronze is tin. And the proportion, once again, as we looked at for steel, the proportion of copper to zinc also affects the properties of the alloy, and in this case, the color. So brass is a very golden yellowy color, and we mentioned before the copper has more of a salmony pink color. And this bright golden color is what makes it very attractive in costume jewelry. It's also a lot more inexpensive than gold, and of course that means that that's an advantage of using this. If we change the proportion, we get 15 to 20% of the alloy being zinc, then we get a more reddish brass, and this can be used for enamel type jewelry. The increasing zinc content makes it a stronger and harder alloy than just the native copper itself. And so increasing the proportion of zinc increases the hardness and also the tensile strength. And you may also be aware, those of you who are musicians, may also be aware that brass is actually one of the groups of musical instruments in the orchestra. And when its property of being able to be highly polished and very reflective also makes it very nice as an ornamental substance and for musical instruments, trumpets, trombones, tubas, those sorts of things. Another one we'll quickly have a look at is solder. Solder is an alloy of tin and lead. Again, that presence of lead, which we now know is carcinogen, is a bit of a problem, but the use that we make of lead in solder tends to keep it more away from us rather than certainly something that we're going to cook with. And as with the other alloys that we've looked at, the proportion of lead and tin affects the properties of the alloy, and in this case, it's the melting point that's very critical. And the interesting thing about solder as an alloy is that its melting point is usually less than either of the two metals that make up the solder. Now that's very important because solder is fusible, and the fact that it has a low melting point and high electrical conductivity means it's a substance that's used very often in joining wires and other electrical components and circuits. So this is a really useful alloy for electric circuitry. Its proportion of lead and zinc can affect the sort of time that it can spend in a liquid phase, and there's certainly some differences between, say, some plumbing uses where there may be some advantage in having it remain slightly liquid for slightly longer so that you can move things into position before it actually sets, and in electrical wiring where you want it to set very, very quickly. So the sort of question that you might be asked around this particular topic is to explain how the use of a named alloy relates to its properties. Now what you need to do is you need to name an alloy. So you wouldn't want to just put steel, you might want to put something like stainless steel. But here's an example that I haven't talked about that you might find interesting and hopefully a little bit relevant too. Because you may be carrying around a few dollar coins, either the ones or the $2 coins, and these are made from a particular type of bronze. Now bronze is a copper alloy, and we know that we can add tin or zinc to copper to produce bronze or brass. We can also add aluminium, and if we add aluminium we get an alloy of copper called aluminium bronze. This has a composition, and again, because it's an alloy, it can vary, but say, let's call it about 92% copper, 6% aluminium, and also a little bit of nickel in there as well. The interesting thing is that the presence of aluminium, aluminium being very reactive, actually reacts with oxygen and forms an aluminium oxide or alumina barrier. And this actually prevents the underlying copper alloy protects it against corrosion. So these particular types of alloys are very resistant to tarnish or corrosion. They're also resistant to changes in their nature if they're exposed to salt water, higher temperatures. They have a very high strength, which means we can have them jingling around our pocket, banging against other coins in cash registers and so on. And they retain a very nice golden color, which gives them a little bit of an appeal as well. So when you're looking at your named alloy, make sure that you identify which one you're talking about and ensure that you're relating uses and properties. So what is it about the specific alloy that makes it suitable for the use that you've chosen? Thanks for listening.